Hello everyone, I am Anmol Singh with Varinder Singh and Shivam Sharma, and today we are going to present our presentation of electronics assignment on design, analysis and verification of discrete amplifier and oscillators, which will focus on common source MOSFET amplifiers and Wien bridge oscillators. So let's begin with the problem 2, which is common source CS MOSFET amplifier overview. The common source MOSFET amplifier is a fundamental single stage amplifier renowned for voltage amplification capabilities and inherent 180 degree phase inversion. The problem focuses on its detailed analysis and verification. So let's begin with the introduction. Analysis of fundamental single stage amplifier for a voltage amplification with 180 degree phase inversion, and the design objectives are analyze mid-band gain, cutoff frequencies and bandwidths using hand analysis and LT spice verification. So the circuit parameters are voltage is 1.8 volt, resistance is 3.41 kilo ohm, and resistance in series is 1.39 kilo ohm, and resistance G1 is 852.5 kilo ohm.
Now here problem 2, effect of source bypass capacitor. In this we see that the capacitor is bypassed by automatically. In this experiment, common source series capacitor. In this investigation of frequency response with CS removed effectively, creating a connection source amplifier with source degradation. In observation, significant decrease in mid-band gain and increase in the lower cutoff frequency. And at the last, we conclude that removing common source introduce source degradation and negative feedback, which improve stability and linear but reduce voltage gain.
So in the next problem, we have a Wien bridge oscillator, which principles when the Wien bridge oscillator is classic circuit for generating stable sinusoidal waves distinguished by its frequencies, selectively RC network and positive feedback loops. Understanding its operational principle is key to achieve the desired oscillation frequencies. While introduction this utilize a frequency selective selection RC networks with a feedback loop to generate stable sinusoidal waves. In the resonant network, the Wien bridge network provides zero phase at the resonant frequencies, crucial for the sustained oscillations. In the gain conditions, for stabilizing the oscillations, this amplifier gain must be precisely act to compare. So in the transient analysis and loop gain settings, the stable and waveform purity of a Wien bridge oscillation are highly dependent on its loop gain. By adjusting the feedback network, we can observe the critical impact of loop gains and oscillations. Like as we see in this diagram, we have three cases. First case is when R1A is 35 and R1 is 15K, and after that this in second case the R1 is 32 and 18, and in third case the R1 is 25 and 25. So when the R1 is 25 and 25, the loop gain will be greater than 1. So the oscillations cannot be sustained, leading to the decaying output. In the second case, when the R1 is 32 and the R2 is 18, the loop gain will be equal to 1 and stable oscillations will be minimum distortion. And in the last case, when the case is that we have R3 35 and R1 is 15, then the loop gain will be less than 1. So in the next slide we can see the graphs that we have been plotted for that, and after that there are key takeaways that the difference between the amplifiers and the oscillators.
In these, the CS amplifier source degradation implemented by the unbiased resistor in the source path, introductions, negative feedbacks. The effective reduce the voltage gain, but they dramatically enhance the amplifier linearity by migrating harmonic distortion. It also improves input and output impedance control, contribution to overall circuit stability and bandwidth, especially at the higher frequency where the passive capacitor starts to dominate. In the in-vein bridge oscillator, the vein bridge oscillator relies on the precise balance of positive and negative feedback. For sustainable, stable, and undisturbed sinusoidal oscillator, the loop gain must be maintained at exactly unity A beta is equal to 1 with a 0 degree phase shift. In this deviation where the loop gain is greater than 1 lead to grow distortion waveform, while a loop gain less than 1 cause oscillator to decay as clearly demonstrated in our LT-SPICE simulation. We achieve the critical unity gain and require carefully component selection and the often and the amplitude stabilizing mechanism.
So the role of feedback. The both negative and positive feedbacks are fundamental tools in the analog circuit design. Negative feedback explains by the source degradation in the CS amplifier improve the linearity, stability, and often bandwidth through the cost of the gain. Power positive feedback critical for the weighing bridge oscillations is essential for generating oscillations or creating regenerative circuits. Understanding how to apply the control these feedbacks mechanism is permanent for designing functional and robust electric systems with desired characteristics. Finally, we conclude and future walks will be theoretical validations. The theoretical calculations for both the circuits were successfully validated using the LT-SPICE simulation, conforming analysis and a model analytic model.
In this impact of feedback, the importance of feedback, especially a degradation in amplifier and precise loop gain in oscillation, was clearly demonstrated. In these future directions, they explored active gains control for the vein bridge oscillator to dynamically maintain optimal loops gain for stable output. At last, advanced application investigate the integrity of these fundamental blocks into more complex systems such as phase lock loops or audio processing circuits.
So this was our presentation. Thank you all.
Do we check out the V out? Now we run this circuit. Shivam run the circuit. No. Yes. Click on V out.
Here.
Zoom. Now here you see the circuit in this they reach at approximately 42 decibel mid band gain, and we now simulate the problem 4 also. Now here is now problem 4. We demonstrate it. Shivam, run the code.
Sure.
Click on V out. Now here you see the V out increasingly.
Like here we have given the values. It is 18 and 32. So we have discussed earlier that when the values will be 18 and 32, the value of the voltage will be below below 1 volt. So this is showing that this is the value is below 1 volt.
Now we also show you the word file also. Now here is one word file in which we
have done the main
we have
calculations.
done the all the questions and its problems. Now here is this main circuit, and this is the component used in the problem 2. Now we all detailed theory. Now this is the part. Here you see the output like 42 decibel mid band gain. Now next, here is the all calculations. No, next. Here is the mid band gain. Finally, we above. Here here after the calculation we get the 41.9, which approximately 42 decibel near. Now here we also get the lower cutoff frequency graph, which surely like increasingly V out. And next here we get above here we get the mid-band gain like 42 decibel and minus 3 decibel level, which means 42 minus 3, which approximately minus 45. And above here finally we get the lower cutoff frequency is FL 1.55 hertz. Now higher cutoff frequency as on the formulas base. Now next now here is problem 4.
So now in the problem 4, we have been given that we have to just make this simulation, and after that we have to just put the 3 different values in the simulation mode and take out the values. So in this is the simulation that is made in LTSpice, and after this we have just this is the first output when the value of the is 18 and 32. And when this is given as the RA is given as 15 and it is given as 35, then the you can see the graph like it's going downside from 1 volt. And in the similar case, when when it's the 25 and 25, then the output is going as constant as 1. It reaches the 1 after a delay of time. So after this we have concluded that the weighing bridge was analyzed with both the theoretical terms and the calculations terms in LTSpice simulations also. Hence the calculations confirms that the oscillation frequency of approximately 1 kilo ohms, and my answer was 9.9 something. So it was nearly to 1 kilo ohms kilohertz. So this conclusion is also concluded. Thank you.
Thank you very much. Bye bye.